People who skip listing the actual outcomes end up with probability calculations that drift, and their decisions start ignoring real risks. The misconception is thinking a distribution is a vibe or an average, not a precise assignment to every distinct possibility. Mathematically, that means mass gets thrown onto overlapping labels, some cases get no mass at all, and nothing enforces that the total covers the space exactly once. You run an online experiment, track a few headline events, feel confident, and days later the dashboard shows contradictions that should never coexist, but you cannot tell where the leakage came from. A discrete probability distribution is nothing mystical. It is a map from a clearly listed set of outcomes to shares of certainty. Think of a tidy checklist where each line is a single outcome described with no ambiguity, and next to it sits the share of certainty you assign it. The map covers the entire set, and only that set. This is the object your inference rides on, not the raw data sample, not the storytelling around it. Use a real category set to anchor the idea. Suppose you describe tomorrow in coarse weather words like sun, cloud, and rain. A discrete distribution here is the mapping that assigns a share of certainty to sun, a share to cloud, and a share to rain, where these descriptions do not overlap and together they cover what you care about. That is it. A table with labeled rows and shares that express your beliefs or the frequencies of a stable process. Beginners routinely break exclusivity and exhaustiveness without noticing. Labels like showers and cloudy can overlap, so the same day is counted twice. Or they forget to include edge cases like fog or hail, which means some outcomes float unaccounted for. When you later try to compute the chance of a plan that requires dry conditions, you cannot add up clean shares because the map itself is incoherent. The correction is boring and essential. Define the support precisely, make labels mutually exclusive, and ensure the shares add up to 1, with none negative and none above 1. If a case is impossible, give it 0. If a case is certain under your conditioning, give it 1. Write down the set in plain language. Check that every real-world observation you might see lands in exactly one bucket, then assign shares and verify the total with a quick audit. This step is not busy work. It is the difference between a model and a list of vibes. What does breaking these rules cost you in practice? It gives you probabilities that cannot be used in downstream logic without hacks. You will see inconsistencies when you try to combine events, compare strategies, or simulate outcomes because the map keeps smuggling in overlap or gaps. Worse, it erodes trust since collaborators start catching exceptions that look like bugs but are actually the footprint of a sloppy distribution. Another reliable trap is assuming equal likelihood because you cannot think of a reason not to. Equal shares are not a default. They are a claim about the mechanism that produces the outcomes. Website visitors do not arrive equally from every source, product options are not clicked in equal measure, and a survey does not reach every demographic equally. When you flatten these differences, your conclusions privilege the rare and downplay the common or vice versa, depending on how the skew actually runs. The fix is to model the mechanism first, and only then reach for shares. If you genuinely lack mechanism knowledge, estimate the distribution from data by counting how often each outcome appears and normalizing by the total counts. When the sample is small, treat the estimate as a starting point, not a truth. You can introduce prior structure or smoothing in a principled way later, but the key move right now is to respect the map and normalize pattern. Every time you reestimate, check your labels, the coverage of the set, and the normalization, because drift loves to sneak in at those edges. Events live on top of the outcome map, and here's where people secretly switch to hand-waving. An event is a set of outcomes that satisfy a description, like dry weather or any traffic from paid channels. To compute its probability in the discrete world, you add the shares of the listed outcomes in that set, and you do not invent new shares for the event itself. If you find yourself tempted to multiply or divide because the description sounds compound, stop and ask whether you are adding over outcomes or working with independent repetitions. Those are different structures. There are two helpful pictures that keep your intuition honest: the mass function and the cumulative view. The mass picture is the bar chart over your outcomes, 1 bar per outcome, sitting at the height of its share. The cumulative picture is the staircase that, for any ordered set of outcomes, tells you how much certainty you have accumulated up to and including a cut point. The mass picture is what you need for clean event sums. The staircase is what you reach for when you care about thresholds or at most statements. Discrete and continuous settings behave differently at the atomic level, and mixing them up ruins calculations. In a discrete distribution, a single outcome can legitimately carry positive probability. In a continuous setting, a single exact value has probability 0 and only ranges matter. Do not read off a density value as if it were a probability, and do not treat a discrete bar as if you needed a range around it to give it weight. Keep the pictures separate and your rules will stay consistent. Under the hood, a distribution is an instruction sheet for averaging. Give it any function of the outcome, and it tells you the long-run average of that function by weighting each outcome by its assigned share. That is how you turn a probability map into an expectation for cost, reward, or risk without simulating. The accuracy of that average rests entirely on the same two pillars you keep hearing about: a correct support and a correct set of shares. Joint discrete variables add one more layer that looks harder than it is. You extend the map to a grid where each cell is a pair of outcomes, like device type crossed with region, and each cell gets its share. Marginal distributions are what you get by summing over rows or columns. Conditional distributions are what you get by restricting to a row or column and renormalizing. Independence is a special case where the grid factorizes into separate lists, which you can test by checking whether each cell share matches the product of its row and column shares under that model. Sampling from a discrete distribution is the mirror image of reading from it, and it is a good discipline check. You can sample by spinning a wheel partitioned according to the shares, or by walking the staircase upward until a random pointer lands in a step. If your implementation drops or duplicates outcomes, the wheel will have gaps or overlaps, and the samples will expose it immediately. Thinking in terms of a wheel or a staircase anchors the abstract map in a concrete mechanism you can test. Finally, naming distributions is often just shorthand for common maps that share a structure. A categorical distribution is the generic map over labeled outcomes. A geometric distribution maps counts of tries until the first success. A Poisson distribution maps non-negative counts when arrivals are memoryless in time, and each of these is just a specific way to set shares across an infinite or finite list. You do not need the names to build a correct map, but the names help you import known properties when the mechanism matches one of these templates. The real shift is to stop treating probability as a loose feeling and start treating it as a fully specified map over a space you have written down. Once you commit to exclusive labels, exhaustive coverage, and clean shares, every other idea and inference plugs in without friction. You quit guessing, you start auditing, and your answers stop moving when the story around them does. Next, we use this map-making habit to count outcomes across repeated tries with the binomial distribution, which gives you the probability of each possible number of successes when you repeat the same trial over and over.